All right, so first question is a what? Not a difference, but a, yeah, of course. I know, it's a habit, right? Difference of squares. So a sum of cubes, and this is something we talked about when we first learned it. It comes up over and over and over and over and over again. For those of you taking calculus, it comes up again in calculus over and over and over. It is something that does not go away. So we need to know it. This is a really simple one. We're just using the formula, but this is a good example of how the formula works. So you take the cube root of the first term and the cube root of the second term. So, cube root of 8 is 2. And the sign between them is the same. If this was a difference of cubes, we'll see a difference of cubes coming up later, a bit of a harder one, but we'll see that after. If it was a difference of cubes, it would be y minus 2, right? And then, again, the formula is square the first term, opposite sign from the first bracket, multiply the two terms together, so 2y, and then the third term is always positive, and it is the second term from the first bracket squared. And that is just a formula, right, that you kind of have to memorize. It's not something that you're going to make up on the spot. In fact, when we did it, we didn't derive it, we didn't do anything like that. We only noticed it as a pattern, and only briefly, really. This is another sum of cubes. It's a little bit different because it's got two variables and sort of more coefficients and more stuff going on. And it's got a 6. One trick is you could do this in the question, or you could do this on scrap paper, is try to write out what are the two terms that are being cubed. So the second one's a bit easier. 27y cubed is 3 cubed gives you the 27. And y cubed obviously gives you y cubed. For the first term, it's 2 cubed gives you 8. What cubed gives you x to the 6? Jasper. So this is x squared. All cubed gives you x to the 6. So that's your A and your B if you're thinking about the formula. And so we take this and we go 2x squared plus 3y. That's how we get that. It's just a way of focusing your thinking when things are a little bit trickier, figuring out what your A and your B are. Okay, then it's the first term squared. And you could write this out. I'm not going to. I'm going to do it. But you could write out 2x squared squared and take an extra step if that helps. But 2x squared squared is 4x to the 4th. Change the sign. Multiply the two terms together. 2 times 3 is 6. X squared y. 3y squared is 9y squared. 3y all squared is 9y squared. Remember, we talked a lot about observations throughout the whole course. In some places we talked about them more than others. When we did identities, we talked a lot about it. But any kind of question is the same thing. You're kind of stopping and you're analyzing. In particular, imagine on an exam where all the units are mixed together. Now, as I said, they're kind of in order on our exam, but some of the questions are mixed up with each other. And so you could come to a question, you got to analyze it. You got to figure out, what kind of a question is this? What do I have to do? Now, the instructions say to factor, but there's all different kinds of factoring. So when we sit here and look at this question, what kind of factoring is it? What do you think? You don't have to name it. You can describe it. What's the first step? Yep.
You have to find out what x value will make the entire thing 0.
Yeah, so this is the one that we learned in Unit 1, how to factor fully. Well, this is Unit 1 review, so that makes sense. And then we used it a lot in Unit 2 and throughout the rest of the course. And the first step is to go hunting for a factor. If this was actually done in Unit 1, now you don't have to go back to this form, but I'm going to do it that way just to sort of link into those memories that we have from Unit 1. We would do something like this. Let f at x equal that. And we would go hunting for a factor that makes this expression equal to 0. And one of the things, remember, we talked about was just look at the coefficients. Is there any way to add and subtract the coefficients together to get 0? 5 plus 3 is 8, plus 4 is 12, minus 12 is 0. And the 5, the 3, and the 4 are positive, and the 12 is already negative. So f at 1 equals 0, right? So there's an easy factor to find, and often that happens. Therefore, what? It's funny to think back how much we did this and how familiar it was at the time, and then you're like, yeah, I remember, like it's right on the tip of my tongue, but I can't quite pull it out exactly how to say it. And again, that's okay. That's where we're at right now.
X minus 1 is a factor.
Very good. X minus 1 is a factor. What do we do next? Synthetic division, or whatever kind of division. Remember, there's other tricks, other ways of doing it. But exactly right, synthetic division is probably what you're going to do next. Write out the coefficients, 5, 4, negative 12, and 4. Set up those two lines. We haven't done quite as much of this lately, but we did a lot of it early on.
Oh, I can take the...
Oh, that should be a 3. Is that what you were going to say? Is that what you're going to say, son? Yeah, thanks. I don't know why I wrote 4. Okay, pull down the 5, multiply by the negative 1, subtract 3 minus negative 5, so 3 plus 5, that's 8. 8 times negative 1. Subtract negative 12 minus negative 8, negative 12 plus 8, negative 4. Negative 4 times negative 1 is 4. 4 minus 4 is 0. Put that 0 in a box. What does the 0 represent? No remainder, which is what we want because it's supposed to be a factor. That's the whole point. That means x minus 1 is a factor. If you got anything other than 0, you made a mistake in the synthetic division or in this, finding that factor. The factor you found wasn't actually a factor, right? Now we can take those three numbers as coefficients and write out the rest of the factor form. What's next? Yeah, and I mean, sometimes people get caught up in the grade 12 part and they use factor theorem again to do this, and they go hunting for a factor and use synthetic division, but it's probably easier to factor it the grade 12 way. Is it going to be 1 and 4 or 2 and 2? I think it's going to be 2 and 2 because 2 times 5 is 10. 2 times 1 is 2. 10 minus 2 is 8. So it looks like I want the 10 to be positive and the 2 to be negative so that we get positive 8. Good? All right. D. Now this is a tricky one. This is a little bit beyond probably something you would see on the exam, so I wouldn't panic about it. But if you can do a question like this, that makes all the other simpler ones that much easier. So this is the one that kind of pushes our algebra skills, pushes our conceptual understanding of really what's happening here. Okay? Again, you just have to come up with your A and your B. A minus B, where A is the thing that's being cubed and B is the thing that's being cubed. So if my A is the thing being cubed, which is x plus 2, and my B is the thing being cubed. Notice this is a difference of cubes, by the way. Right? We're subtracting this time. Is x minus 3. We get x plus 2 as our A and x minus 3 as our B. A cubed minus B cubed. What's your A? What's your B? In this case, they are binomials. I'm going to change those to square brackets just because it's going to make it a bit clearer. You don't have to. Then the formula says it's A squared. So x plus 2 all squared. Flip the sign. Compare that to the first two questions that we did, where the first bracket was plus and the second bracket had a negative in the middle term. And this one's got a minus and then a positive in the middle term. A times B, so my A is x plus 2. My B is x minus 3. Third term is always plus, and the B and squared. And now we have to expand and simplify. X plus 2 minus x plus 3, right? Expanding the negative through that bracket. X plus 2 all squared. Now take as much time as you need to do this. But this is why back in grade 10, you are challenged to start getting used to the formula of squaring a binomial as opposed to actually writing it out like this. And doing the whole thing. If you can do it in one step like I did there, which by grade 12 I think that's pretty reasonable, it just really speeds things up. If you have to slow down for everything, it just takes that much longer. By the way, this is a mistake that happens. People say x plus 2 squared is equal to x squared plus 4. They just square each of them. That's like distributing an exponent into the brackets. And it's amazing we still make this mistake. People still make this mistake in calculus. This is a big mistake. This is a grade 10 mistake. You got to find a way not to make that mistake anymore. X plus 2 times x minus 3 is x squared. 2x minus 3x is negative x. 2 times negative 3 is negative 6. X minus 3 all squared is plus x squared minus 6x plus 9. Again, expanding it kind of with that formula, that pattern that we should know by now. X minus x is gone. 0. 2 plus 3 is 5. All right, now we're collecting like terms. What do we have here? X squared plus x squared plus x squared is 3x squared. Negative 1 minus 6 is negative 7 plus 4 is negative 3. 4 plus 9 is 13, minus 6 is 7. Sometimes you end up with a common factor in there. And you have to take that further and factor it out because it says factor fully. So at any point before you're finished, if there is still a common factor or still something that can be factored, you need to factor it. Or what if you could factor that as a quadratic? It's a trinomial. Anybody have a comment about that? So something that we learned is when we do sum or difference of cubes, that trinomial is never factorable. But there's a quick check. If you're not confident, Mr. Belair said something about it never being factorable, but maybe with one of these tricky ones, it could be factorable. B squared minus 4ac, the discriminant, you could quickly check and just confirm for yourself that that quadratic's not factorable. And it's not, so we're done. Okay? If you want to take a second to get started, if you know how to do this, go ahead. You can start rushing forward. I'm going to just wait a short time, give you a chance. If you're watching the video, you can pause it and give this one a try if you remember how to do it. This was one of the questions that's on the exam. Okay, how do we get started? Yep. X-intercept. So we got one here, and one here. And we're going to write them out like this. What do I put next? Anybody remember? Yep. X plus 3 squared, because this is a turning point, x-intercept, at -3, so it's x plus 3, good. Next one. Straight pass through at -1. So that's x plus 1 to the 1, which obviously you don't have to write. Next one is at +1. And it's a cubic twist pass through. So x minus 1 cubed. But we missed something. What did we miss? The a. Right? That's what makes it a family of functions. That's the only thing. And if you remember, I don't know if you remember the demo, but I showed a demo where if you change the a value, you don't change the x-intercepts. You just kind of stretch the graph and compress it, and you can even flip it if it's positive or negative, that kind of thing. But those intercepts don't tell us anything about what the a value is. It's the only thing that's missing. And that's the whole point of this question, is to write it out, show that you understand the order of the x-intercepts. So what are the x-intercepts? How do you write them as in brackets, as binomials, as factors? And with what exponent do you put? But then also, how do you find the a? Which is kind of the bulk of the marks. So if you forget to do that part, you kind of lose a lot of marks. How do we do that part?
You substitute in a point.
Sub in a point. Now this question doesn't have a listed point. The rule of thumb was, if the point is not listed, then the y-intercept is a perfect point. So what is that y-intercept? It's 0, what is that, -3? The question on the exam has the point listed, so there's no confusion. Sometimes people do a silly mistake and they put in -2 instead of -3 or something like that, or +3 just by accident. So to avoid any of that, it's given on the exam. This looks like a perfect point, and it might well be, but you can't assume that. It's the y-intercept. That's just a classroom rule. That's not a universal rule. Okay? What's the other thing that we want to notice about this? Anybody have any thoughts? Yeah, the end behaviors, so it goes from quad 2 to quad 1, the end behaviors are both pointing up. That means A is going to be positive. You don't have to do anything about that. It'll work itself out, but that's your check at the end that you've done it correctly. So let's sub in. Negative 3 equals A. 0 plus 3 is 3. 0 plus 1 is 1. Minus 1 is negative 1. Negative 1 cubed is negative 1 times 3 squared, which is 9, is negative 9. Divide both sides by negative 9, and you get A is equal to a third. And then the other thing, the other little tip or reminder is don't forget to write out the answer. Notice that it did work out to be positive, like we just talked about. How's that? All right, moving on. So again, we're going to have a whole bunch of questions that are kind of mixed up. If you remember the test from, so this is, we're getting into Unit 2 now. You remember that test? It was all solving, and all the questions were kind of mixed up. Solve this absolute value question. Solve this polynomial inequality. Solve this absolute value inequality. Solve this polynomial equation. Everything was kind of mixed up throughout the whole test. So again, you have to identify the type, and you really have to remember that there's all these different techniques and strategies. It's amazing when we start to get into this exam review, and you look back at how much we accomplished. And that's always true. I find that's true of every kind of math class. But like you start going like, oh yeah, I remember doing all of that. Oh yeah, all of that too. Like, holy cow. We covered a lot of material. Kind of interesting to reflect. Anybody have any thoughts on how you solve a polynomial inequality? It's a very specific and different technique that we learned how to do, that we used, that we've never seen before. We sketch it, and we read our answer off the sketch. Okay, very good. So off to the side here, I'm going to sketch it. This is an awkward one. It's got a couple of fractions in it. Makes it a bit harder. That is negative 1. That is negative 1/3. And that is positive 5/3. So negative 1 is the sort of one that's over here the most. And then negative 1/3. And then positive 5/3. Now you have to think about the degree and the sign of the leading coefficient to determine the end behaviors. This is degree 6, so both up or both down. Remember, if it's an odd degree, it's 1 up, 1 down, one way or the other. Even degree is both the same. And positive leading coefficient, because this would be 3 times 1 times 9, because that would be 3 squared. So this would be 27x to the 6 if we were doing that partial expansion. Again, this is something that some people find a bit tricky. It's not something that you have to be able to do. It's just a way of thinking about what the the leading coefficient would be if it's positive or negative. We don't need to know that it's 27. We just need to know that it's positive. Negative 5 times 1 would be, I guess, minus 5. That's going to be our y-intercept, which again is useful as a check for the sketch. That we have our x-intercepts in the right place and our end behaviors in the right place. So this is going to start again in quadrant 2. First one is a straight pass-through. Oh, what happened? Next one is a cubic twist pass through. Oh, that didn't look very good. Nope, sorry. I got the wrong one. I was looking at them in order. Next one is, oh, this is the cubic twist. Oh my goodness. I was looking at them in order from left to right, but. And then this is a turning point. Oh, and then there's your straight pass through. Sorry, I have to do that again. Okay, so there's your -1. There's your -1/3. And there's your 5/3. And I knew I was making a mistake because the way I was drawing it the first time, I was going to get a positive y-intercept, but it should be a negative y-intercept. So there's the value of checking the y-intercept because you can catch your mistake. Now, how do we read our answer? Where is it less than 0? Looks like in this section and in this section. It's strictly less than, not less than or equal to. So I don't include the point of -1/3. I have to write this in two separate answers. So from -1 to -1/3, and from -1/3 to 5/3. Notice the next one's the same function, so we don't have to do all that work again doing the sketch just to speed things up. But now it's greater than or equal to 0. So now we're going to go back and read the graph and notice that it's greater than there and greater than there. So when x is less than or equal to -1, there's another little trick here. Yep.
Is that like when x is equal to
Yeah, because this says greater than or equal to 0, and it's not ever greater than, but it is equal to 0 at that point. So we have to include it. So there's 3 places for that one. There's not going to be a lot of repetition on the exam. So you're not going to get a bunch of the same kind of question. The questions are all very different. For example, if the question that says fully factor is degree 3 polynomial like the one that we saw on the last page, you're not going to get one like that in the solving equations. It's going to be different. There's not going to be a lot of repetition. So what makes this one different? Because it looks like a cubic, so it looks like we're just doing the same thing. Again, even for the in-class review, every question is going to cover different concepts. It's not worth it for us to waste our time sitting here together and go over the same thing over and over and over again, really. I guess there's going to be a little bit, but. So this one has a common factor. which makes it kind of look like not really a grade 12 question, because there's like, now we're going to just solve a quadratic equation. But there's a very specific reason why this question is here, and that's because b squared minus 4ac is 880. So what does that mean? Square root of 880 is not a perfect square. So quadratic formula. X equals 0, sometimes that solution gets forgotten. People jump right into quadratic formula and forget to state that, but you need to state that. And x equals negative b plus or minus b squared minus 4ac, which we already calculated. So as long as you show that off to the side, you can go straight to that step. All over 2a. 2 times 5 is 10. $880, whoops, is divisible by 16. Now that's a guess and check. You'd probably guess that it's divisible by 4. I hope you would. 8s are divisible by 4, probably 808. I mean, you can look at that and determine it just in your head. But even just looking at those numbers, you would guess, and you can use your calculator if you want. And then what I would do is I would check 16. And then I would check 64. And like keep checking. When you divide it by 16, you get 55. You can see that 55 does not have a perfect square in it. So then you know that 16 is the biggest. 220 also looks like it could be divisible by 4, which it is. That's why 16 is the one that works. So like, you know, try 4 and look at 220 and say, oh, I think maybe I could go bigger. Try 16, and then when you get 16 and you see that 55, that's when you could stop. Or if your numeracy isn't quite at that level, it's a guess and check method to try to kind of try different perfect squares and see which one is the biggest. Square root of 16 times the square root of 55. Remember, this is how we do simplifying radicals. And then the whole point is that we can actually take the square root of 16. I can divide a 2 out of every part. So you can do this in one step, and a lot of people have a calculator that will do this for them, and that's fine. You don't have to show these steps. So I'm going to factor out a 2. 2 is the biggest one that we can do. So minus 10 plus minus 2 root 55. You could factor out a 4 from the top, but 4 won't divide into 10. And then the 10 and the 2 divide. And that's our final answer. And probably the question would ask for exact value, so you would leave your answer like that. If you needed the decimals, that's something that comes up in trig. You know, put that into your calculator. You can do that, but we'll leave that one for now. So the point of that example is quadratic formula, b squared minus 4ac, sort of reviewing all of that, and then reducing the radical as well. Okay, D. So this one does look a lot like the one from the first page. There's nothing different about it. So a little bit more practice with factoring higher degree polynomials using factor theorem. That's what this one is. So we'll dive right into it. what I'm looking at is the coefficients 2, -5, -4, and 12. They do not add or subtract. There's no combination of them. 5 and 4 is 9. 9 plus 2 is 11. So that's not enough to cancel out with the 12, no matter what you do, right? So 1 or -1 won't work. So what about 2? 2 times 2 cubed, which is 8, minus 5 times 2 squared, which is 4, minus 4 times 2, which is 8, plus 12. Oh, there's your 0. So positive 2 worked. And the first example, we did all that extra notation stuff, but you don't have to do that anymore. So x minus 2 is a factor, so we can just write it down off to the side. And again, I'm going to give you a second. Why don't you try this synthetic division by yourself? Yes?
Wasn't there like a trick to do these that you don't need synthetic division?
Yep. Do you want to see it? So the trick goes like this. We know this is going to be an x squared term, and it's only going to come from x times whatever that is to get that. So it has to be 2x squared. X times 2x squared gives you 2x cubed. Then this is negative 4x squared, but I want negative 5x squared. So the next one has to be negative 1 to add to the negative 5, to get negative 5. That's the trick, like right there. If you can figure that out and do that, that's how the whole system works. You look at the information you already have, and you think about what you have to add to it to get the result that you're looking for. So same thing, now I'm looking for negative 4x. I've got positive 2x. So what do I have to add to positive 2 to get negative 4?
-6.
So minus 6. And if we do the synthetic division, I bring down the 2. Well, there's your 2. 2 times negative 2 is negative 4. So negative 5 plus 4, because minus negative 4 is negative 1. Negative 4 minus 2 is negative 6. There you go. And there's your check. Now the check in this method is negative 2 times negative 6 gives you positive 12. So there's a check in both methods. That tricky method is a little bit faster if you've got good number sense and you're able to kind of hold all those numbers in your head. But some people just prefer to stick with, a lot of people just prefer to stick with synthetic division. Now we would probably check b squared minus 4ac again. So b squared is 1. When I multiply the 4ac, c is negative. So this is actually going to be plus 4 times 2 times 6. 49 perfect square. So that's factorable. Probably 3 and 2, right? So let's see. If I put the 3 here and the 2 here, I get 4 and 3, which gives you the 1. And I want the 4 to be negative. Oh, look at that. So we only have two solutions. Oh, negative 3 over 2. All right, moving right along. Couple more from Unit 2. Double absolute value equation. So I'm going to go over this one. I would expect most people remember kind of doing this, but maybe don't exactly remember The process, of course, if you're watching the video and you do know how to do it, you can pause it and do it yourself. But if you remember, what we did was we wrote the two sort of factors from the brackets on the side. Then we drew a line sort of straight across the page. And we mark these aren't x-intercepts, but we're thinking of them as x-intercepts, and we're thinking of this as a number line. So what would be the x-intercept that goes along with that? -2. And with the other one is +4. So this is the interval of x less than -2. This is the interval of x, of -2 less than or equal to x less than 4. And this is greater than or equal to 4. Where do you put those equal signs? It's not important, but you have to include the -2 and the 4 somewhere. You can't just ignore them. You could even include them in both technically, although I think some teachers don't prefer that. Okay, now, anybody remember what we do now? It's coming back at all? Danielle? Yeah, very nice. This is where we start to do the interval testing. Remember, this comes up throughout the unit or the course in other areas as well, right? Solving other kinds of things. We do this interval testing, and it's going to come up in calculus too. So I picked some number to represent that interval. Remember, -10 was the number that we often picked. So -10 plus 2 is negative. -10 minus 4 is negative. How about 0 for the middle interval? 0 plus 2 is positive. 0 minus 4 is negative. And again, how about 10? +10 plus 2 is positive. And 10 minus 4 is +6, so positive. They don't always work out like this, but a lot of the questions did. But there were a few that were sort of, set up differently. There were slightly different kinds of questions, and it's not just always negative, negative, positive, negative, positive, positive. So you do want to go through that testing. And because it comes up in other areas, you want to think about it. Okay, so what does this mean that there's negatives? It means that the argument of the absolute value would calculate to a negative. So we have to put a negative out in front to turn it back to a positive, because that's what absolute value does. Okay? And same for both, because they're both negative. In the middle, only the second one is negative, so it's just x plus 2. I leave it alone. And in the third interval, they're both positive, so I just leave them both alone. Okay, go ahead and solve them. Yeah.
Is there a reason why there's a 0 on the last one?
I don't know why I put 0. Thank you. Okay, and what's our last step? Yeah, very good. So what you're talking about, the middle one doesn't make sense. What you're talking about is we're interpreting the answers, right? These may be extraneous, or they may be nonsensical results. And we looked at the visual of what, like, try to make sense of what's happening in this algebra, but that's not something we're going to get into now. But we got to look at all three. Is negative 3 in this interval? Yeah, it is. So negative 3 is a good answer. You can get answers that work out, but they're not in the interval, so they're extraneous. 6 minus 8, well, that's never true. So there's no solution in that interval. Is 5 greater than or equal to 4? Yes. So we have two answers, and we do our therefore statement summarizing what the actual answer to the whole question is. All right, one more. We're moving on to Unit 3. The setup for this one is the same as the single absolute value equations, but this is an inequality, so the setup is the same, but the interpreting the answer or coming up with the answer is a bit different, if you remember. Okay? So we split it up into two cases. When 2x plus 2 is less than or equal to 0, which is when 2x is less than or equal to negative 2 and x is less than or equal to negative 1. This is the case where the argument of the absolute value results in a negative. So we put a negative out in front. Case number 2 is 2x plus 2 is greater than 0. Again, where you put the equal sign on one or the other, or I suppose both. But it's got to be on at least one of them. The argument of the absolute value is positive in this case. This is how we're setting it up. So we don't put a negative sign out front. Now we just solve them. We're dividing by negative 5 here, so we have to flip the sign. Now what do we do? Tricky part of this one is, it's similar concept to what we did before. We have to decide if this is in this interval. The difference with these questions is some of it might be and some of it might not be. The intervals are kind of going to overlap. They're both intervals, so they might overlap or they might not. So if you remember, we used number lines for this. So I'll do a number line for the first one, and I'm going to mark negative 1. And hold on. Yep, negative 1, negative 1/5, and 3. So when x is less than or equal to negative 1, I include negative 1 and go that way. when x is greater than or equal to negative 1/5. I go that way. So what happened there? Are there any numbers less than negative 1 and greater than negative 1/5? No numbers, so no solution for that part. I'm going to do the rest of it below the number line, the second one, just to keep them separate. When x is greater than negative 1, we use an open circle. And when x is greater than or equal to negative 3, use a closed circle. Where do they overlap? They overlap when x is greater than or equal to positive 3. And then sometimes we were doing a second number line. In this case, we don't really have to because one of them is no solution. But if you remember, sometimes we would do a second number line to come up with an overall solution. But in this case, we can just state it. Therefore, x is greater than or equal to 3. Yeah?
I think that's wrong. Was there a trick for this one too or no?
A trick. I wonder if you're thinking about just, you can do it without the number line if you're good with numbers and you just understand what numbers are greater than negative 1 and greater than or equal to 3. Well, numbers that are greater than or equal to 3. Like some people can just do it in their head. You don't have to show the number line. That's probably what you're thinking about, right? All right. Unit 3. So notice we've got one equation and one inequality. And they're very different. This is something that I made a big deal of. The way you solve equations and the way you solve inequalities, just like polynomials, is very, very different. But rational equations and inequalities are even more different than polynomial. Okay? So we'll compare them, I guess, when we're done them both. The equations are the easy type. The equations, you just multiply through by a common denominator. Often what we'll do first is factor all the denominators. That allows us to see what the common denominator is. So our common denominator is x times x plus 3. And in this case, the x's divide out, and we're left with 5 times x plus 3. And in this case, the x plus 3's divide out, and we're left with 4x. And in this case, everything divides out, and we're left with 8. Then we just solve. Anybody remember the sort of last thing that we have to think about here? Again, you can get extraneous answers. In these questions, so you have to think about restrictions and make sure that your answers do actually work and, don't make any of your denominators 0. You don't have to show it. No. Good? The difference with rational inequalities is you can't multiply by the denominator to clear out the denominator. You're not allowed. You have to get a common denominator. Okay? So we're going to bring everything to one side, get a common denominator, put it all together as one fraction, and we're not quite going to sketch it, but we're going to do something sort of similar. Okay? So first of all, I'm going to factor. Do you want to factor the top? I suppose if there might be something that can divide out, then that would make the question more simple. I can factor this in my head, x plus 2x minus 2. That's not going to divide out. So I'm not going to factor it, but it's possible that you could simplify the expression before doing any more work. That's the only reason to factor the top. But I do want to factor the bottoms because I'm getting a common denominator. I already have x plus 3 in the denominator. So for the second fraction, I'm just adding an x minus 3. Oops. How do I do that? Multiply by x minus 3 over x minus 3. Again, you don't have to show this step. So we've got x squared minus 4 minus x squared minus 3x. X squared minus x squared, that's going to be 0. Negative times negative gives me 3x minus 4 over x plus 3, x minus 3. If we compare this to the polynomials where we sketched, and then the absolute value where we were doing interval testing, this is like a mixture of both. So we are going to do a number line. Do you remember what we mark on the number line? So this has an x-intercept of 4 over 3 and vertical asymptotes of x equals negative 3, whoops, and x equals positive 3. So we've got negative 3, four-thirds, and positive 3. And we show the asymptotes as asymptotes. And again, now we do the same interval testing. So negative 10. This is this one where you can do it by inspection. You can put this into your calculator, and we talked about programming your calculator and how you and that makes it easier to do this kind of testing. But negative 10 will make that negative 30 minus 4, so that's going to be negative on top. Negative 10 plus 3 is negative. Negative 10 minus 3 is negative. 3 negatives makes a negative. So that interval is negative. I'll pick 0 for this interval. 0 minus 4 is negative. 0 plus 3 is positive. 0 minus 3 is negative. So 2 negatives makes positive. What's a good number to pick in the next interval. Fractions make it a little bit harder.
2.
Yeah, 2 is probably the best one. It's the only integer in there, right? Can't pick 3. 1 is less than 4/3, so 2. So this is going to be 6 minus 4, which is positive. 2 plus 3 is positive. 2 minus 3 is negative. 1 negative makes negative. And if I pick 10, everything's going to be positive. So positive. So I've got 2 intervals where it is less than or equal to 0. Therefore, one of them is here. That's when x is strictly less than, whoops, I said less than and I wrote less than or equal to, less than negative 3. Why less than and not less than or equal to? Because it's an asymptote, and that's why we draw it that way. Okay, and then the other one is between 4/3 and 3. So this one really highlights that idea. We include x-intercepts, but not asymptotes. That's why one of the ends of the interval is less than or equal to it. It's including the end, but the other one doesn't. All right, only a couple of questions left, but they're big ones. Sketch each function showing the work, that's a bit awkward wording, but anyway, showing all intercepts, asymptotes, and end behavior near the asymptotes. And again, you do have to show all your work. Okay, so remember there's a big process for these, and organizing them in a particular order, a particular set of steps, how you show your work it really, really helps. Right? Kind of having a habit of how you do it. What I like to do first is factor everything, get all the different forms that we want. This is going to be big in calculus. Calculus has more and more forms when we do this kind of stuff. So factor this. So this looks like x minus 3, x minus 1, x plus 2, x minus 2, and I'm also going to let, whoops, getting ahead of myself, let y equal f at x. And I'm doing that because I want to use function notation later in this question. Right? And it's not written out as f at x. Sometimes the questions were. If it's not, you're supposed to do that statement so that we can use function notation. Okay, no holes. We would look for holes here, no holes. So we can move on to intercepts. X-intercepts occur where the top is equal to 0. So that's at positive 1 and positive 3. Y-intercept we're going to get from the expanded form. This is why we want the different forms. Factored form gives us x-intercepts. Expanded form gives us the y-intercept. If I sub in zeros, all the x terms are gone, and I'm left with 3 over negative 4. So negative 3 over 4. Okay, asymptotes. We usually do the vertical asymptote or asymptotes first. X equals negative 2 and x equals positive 2. Where the denominator is equal to 0. Remember, there's all these little bits and pieces about these. How do you find the intercepts? How do you find x-intercepts, y-intercepts, vertical asymptotes, horizontal asymptotes, oblique asymptotes, like all these different things, right? And one of my habits is I like to do things from left to right. It makes sketching easier, makes it easier to go back and find what you need later on, and make sure that you get things on the right side of other things, because if you get an asymptote on the wrong side of an intercept, your graph isn't going to work out. But some people don't bother with it, and that's fine too. Okay, so x equals -2. How do we do testing for vertical asymptotes? Remember what I said when we started? There's so much to remember, and some of this we haven't done in so long, and you were so good at it back then, and you're like, wow, I can't believe I can't really remember this. But it does only take a bit of a refresher, and then you'll have it.
The one where you sub it a little bit above.
Yeah, we just pick a number very close to -2, but just to the left of -2. So how about -2.01? That's to the left because it's negative. Remember, that's kind of tricky. People mess that up. And sub in a number very close to -2, but just to the right of -2, like 1.99. And this is the one where we only have to determine if it's positive or negative. Okay, and knowing how to interpret the answer for each type of asymptote is really important, because if you mix them up, you're going to get it wrong. So -2.01 minus 3 is negative, -1 is negative, +2 is negative, because -2.01 is a little bit bigger than 2, and then -2 is negative. So 4 negatives means this is positive. And -1.99 is going to be negative, negative, and now this one crosses over to positive because 2 is now bigger than 1.99. So we've got 1 positive and 3 negatives, so this one's negative. That means as x approaches -2 from the left, y is going to positive infinity, and as x approaches -2 from the right, y is going to negative infinity. You can try this one on your own if you like. Okay, so that's what I got. Finally, horizontal asymptote. What's the horizontal asymptote? Remember, these have equal degrees, so we're looking at the coefficients of the highest degree term, so it's 1 over 1. So it's going to be y equals 1. Testing for horizontal asymptotes is very different. So we don't approach the asymptote. We find a big value, big negative value for x, and a big positive value for x. Horizontal and oblique asymptotes are as the graph is going way out to the left and way out to the right, as x gets very large, positive and negative, that's where it starts to behave that way, approach the asymptote. So we pick big numbers, we literally sub them in. In this case, you're not just inspecting. You have to sub it in. So you go back up, and this is where you decide, is it worth it to program my calculator, or do I just punch it in? What do I want to do? And that part is up to you. So this is, I'm going to do it this way. Negative 100 minus 3 is negative 103 times negative 101. over negative 98 times negative 102. I can do the adding and subtracting of the little numbers in my head and just punch it in quickly that way. So this is 4 negatives. It's going to be positive. Of course it's going to be positive. The horizontal asymptote is positive. It's approaching the asymptote. Your value is going to be positive. We don't care if it's positive. We care, is it above or below 1? 1.04. So it's above. Okay, and now positive 100 is going to be 100 minus 3 is 97. 100 minus 1 is 99. Over 100 plus 2 is 102. 100 minus 2 is 98. And this one's below. So as x goes to negative infinity, y is approaching 1 from above. As x goes to positive infinity, y approaches 1 from below. All right, now that we have everything, we can make our sketch. Again, there's a lot of practice that goes into these. You don't want your asymptotes to be too far apart or too squished in, like spacing things counts, making sure you don't have an x-intercept on the wrong side of an asymptote, and just what order you do things and kind of how you put all the pieces together, right? There's a lot to it. So I am going to do, just because my ruler is horizontal, I'm going to do the horizontal asymptote first. And don't forget to label everything. I'm going to label as I go so I don't forget. Vertical asymptotes are positive 2 and negative 2. Let's see. Intercepts are 1 and 3, so 1. Sometimes doing your intercepts after is actually a good idea. I'm going to put them in now. The y-intercept I always do after, just so that I can draw a smooth curve and I don't have to like aim at it, if you know what I mean. Okay. And then end behaviors. So as I'm approaching from the left, we're going up, and then from the right, we're going down. So we are up, and then down. And then same thing for the other one. We started up, and then we went down, up to on the left, down on the right. Horizontal, to the left we're above, and to the right we're below. Now we can put the pieces together. So nothing funny happening with this one. Just goes like that. Again, these two make sense because we're crossing the y-axis to get the y-intercept and crossing the x-axis to do an x-intercept. something like that. Now I'm going to mark negative 3 over 4, positive 1. And what's happening here, it looks like we're coming down, crossing, and going that way. Double check that we've labeled everything, looks good. Horizontal asymptote sketch. Remember, only one sketch on the exam, but there is another question about asymptotes. So you got to know all the different kinds of asymptotes. So, what do you think B is going to be? It's going to be oblique. It is oblique. We got degree 4 on top, degree 3 on bottom. So this one's going to be oblique. Again, I'll start by saying let y equal f at x, just so I'm allowed to use function notation. Anybody notice anything about this one? Yep. The whole. So we're going to cancel those out. And the trick with the whole is we notice it, hopefully, and then forget to actually include it in the graph. Okay, so this is x plus 1, x minus 1, x minus 5, x plus 3, x plus 2. Sometimes you could get away without the simplified and expanded version. In this case, we can't because it's oblique and because of the degrees. Sometimes you might be able to, but I like to do it because of habit. I never give hard expanding questions on tests or exams or anything. So, it's not going to be super hard to do. This one's on the verge of being a little bit more challenging. But it does just kind of make your life easier when you start getting into the details. So I wrote the x plus 1 and x minus 1 side by side because that's x squared minus 1. Oops, looking in the wrong place. 5x plus 6. So this is x squared times x, which is x cubed, x squared times negative 5, which is negative 5x squared, negative 1 times x, which is minus x, and negative 1 times negative 5, which is plus 5. And again, we can see that this has degree 3 on top, degree 2 on bottom. So it's still oblique asymptote. It's easier to see an expanded version. We already figured out that it's oblique asymptote. All right, let's get into it. I'm going to move through this one a little bit faster. X-intercepts come from the factored form, plus minus 1 and 5. Y-intercept comes from expanded form, 5 over 6. Vertical asymptotes are where the denominator is equal to 0. So x equals negative 3 and x equals negative 2. Okay, so again, going back and doing the inspection that we talked about before, this one's going to be negative, then positive, then positive, then negative. am I doing? Okay, now this one's oblique asymptote. So what's the process for that? We start by dividing. And this is why we need expanded form. I can't use, if you can use synthetic, it's easier, but I can't because we're dividing by a degree 2 polynomial. Not just because it has 3 terms, but because it's degree 2. Synthetic only works for degree 1. So I have to use long division. So x squared plus 5x plus 6, x cubed minus 5x squared minus x plus 5. It's got to be expanded. It's got to be in the right order. You got to have every term. So remember ghost terms if you need them. X squared times x gives you x cubed. X times 5x is 5x squared. X times 6 is 6x. Subtract. X cubed minus x cubed is 0. That's the whole point. That has to happen. That's why this whole process works. Negative 5 minus 5 is negative 10. Negative 1 minus 6 is negative 7. Bring down the 5. Repeat. X squared times negative 10 gives me negative 10x squared. Negative 50x and negative 60, whew, big numbers. Okay, 0, negative 7 minus negative 50 is negative 7 plus 50, so that's 43. Doesn't matter if they're big numbers, we're not really doing much with them. And 5 plus 60 is 65. Therefore, y equals x minus 10 plus the remainder over the divisor. So for the oblique asymptote, that's this part. We want the x-intercept and the y-intercept. And for the remainder part, I like to define it as r at x. You have to define it as r at x if you're using the notation that we're going to use. You have to define it that way to use that notation. 43x plus 65. And I'm going to write this out in factored form. So that's going to be easier for the testing. Testing is a mixture of the horizontal asymptotes and the vertical asymptotes. We're putting in big numbers for x, like horizontal asymptotes, because the function approaches the oblique asymptote as x gets very large, positive and negative. That's when it happens. But we only care if it's positive or negative because we're not testing the whole function. We're only testing the remainder part. So remember, the actual function has another part to it, the x minus 10. This is going to tell us if we're adding to that or subtracting to that. If we're adding to that, we're above the asymptote. If we're subtracting from it, we're below. You can memorize this. It's helpful to understand it and know why it works. We talked a lot about why it works. And again, if you want to talk more about it, then you can ask. I'm not going to get into it now. But, you can also just kind of memorize it. So when I put in a negative, it looks to me like I get 3 negatives. The top's going to be negative, and both brackets on the bottom are going to be negative. So it's negative. Therefore, we are below. And when I put in a positive, I get 3 positives. So we're above. All right, let's wrap this up. I'm going to do the vertical asymptotes first. This is actually an important thing because you got to make sure that your oblique asymptote crosses them properly. There's a bit of a balance between having things sort of drawn to scale for the most part, but not squishing things together too much. You don't want 2 asymptotes too close to each other, and you don't, especially with an oblique asymptote, you don't want to spread your graph out too much. So, it's a little bit of a tricky thing. Whoop. So this is x equals -3, and this is x equals -2. Now, I've got a y-intercept of 5/6. Yep, that's right. And the y-intercept of the oblique asymptote is -10. So this is going to be a little bit hard to scale because I don't want to put my -10 way down here or anything like that, right? It's got to fit on the graph. You don't probably want to do it like this. Let's say I tried to make it at 45 so that like the scales are equal. Well, that's going to be impossible to graph. Okay, so that's not going to work. So I do have to slant it, and that my recommendation was to slant it a fair bit is going to make it easier to draw. Okay, y equals x minus 10. That's positive 10, that's negative 10. The only reason, to label those is just to make sure that everything is on the right side of everything else. All right, I've got x-intercepts of -1. So again, that's not really drawn to scale, but I did that for a reason. If I squish things up too much or spread things out too much, this would be a really hard graph to draw. +1 and +5. And my y-intercept is positive. Okay, that's going to be important. And behaviors. Where are they? There we go. For the first asymptote, to the left we're going down, to the right we're going up. For the next asymptote, we start to the left we're going up, and to the right we're going down. Oblique asymptote, to the left we're below, and to the right we're above. right, now we get to draw this. So this is squished in here, and that's just the nature of this graph. It always works out that way. It's hard to avoid, but that's why we slanted it. If we didn't slant it too much, we wouldn't even have a corner like this to draw this in, right? So again, you want to try to make your curves as smooth as possible. What's going on with this one? Looks like it's turning like that. How do I know it doesn't do this? Well, because there are no x-intercepts in there. And the question always comes up, how do you know how far down to go? You take calculus. And in calculus, we'll learn how to calculate that point. But for this, you don't, and it doesn't matter. That's not part of it. But in calculus, you will learn how to find that point. That's what calculus is all about. Okay? So it doesn't really matter. If you go down too far, it's probably going to be a little bit harder to draw. So, but don't make it too small either. Just like medium, I guess I would call that. What's going on here? So we're starting down at this arrow. I'm going to draw this once kind of sloppy to talk about the behavior. I'm going to erase it and then draw it again nicely. So it looks like we're crossing through that y-intercept that was positive. That makes sense. Crossing through again. Then what happens? We've got to turn, cross through, and approach the oblique asymptote. So there's a whole lot going on here. But it all does kind of go together and paint that picture, and it does make sense. All right, so let's try to draw this. Whoops. Now what I'm going to do, I'm going to keep my y-intercept fairly low just to kind of keep stuff to scale. And I'm also going to make this curve really low so that I can approach this in a kind of natural way. It's a little bit hard if you go down like this, up like this, you almost have to turn again. This is a pretty intense graph, I would say, that one. Five over 6. There it is. Oblique asymptote, lot going on in that one. Oblique asymptote with 2 vertical asymptotes. It's got a lot going on. So that's exactly right. We forgot about the hole. So we got to go back and erase a tiny little piece of this thing. See if I can get there. Good. I'm going to mark it. And don't forget the hole, which is what we're always likely to do. And it's because you get to the end of these things and you think about moving on to the next question or whatever it is, or whatever else it is that you're doing, and you forget to do it. So mental note, try to find a way, make a hole. Maybe even maybe it would be a good idea to, wherever your sketch is going to end up, make yourself a little note down in that bottom corner that there's a hole instead of leaving it at the top of the page. That's something that you could try. Okay, and that actually wraps up Unit 3.